Now, as the final section in our unit on limits, we'll look at the trigonometric functions. Now, they're unusual because they're periodic, and the first thing we'll notice about them is that they are all 6 of them, continuous on their domains. Now, remember that phrase, continuous on their domains. And let me show you what I mean. Now, I will not prove these. I will just indicate what's happening here. But on their natural domains, the trig functions, as many functions have a natural domain, each function is continuous. Now, this may make you wonder, because you know that some of the trig functions have gaps in their graphs. Well, let's explain. For example, let us go ahead and look at the sine function as x approaches any number whatsoever in the real numbers. We learned earlier that the limit of the sine function is the sine of c. And in fact, that limit, although we won't prove it here, is always true. The limit of the sine functions is sine of c, and so in this context, this statement means that the function is continuous at c. And you know from pictures of the trig functions, the sine function here, that looks something like this, that there are no gaps in this function. It is a periodic function that has no gaps and continues forever in both directions. So this would not cause you any difficulty. You believe that this is a continuous function, and the cosine function is likewise continuous. What about something like the tangent function as x approaches c? Now, the problem here is that as long as c comes out of its natural domain, this will be equal to the tangent of c. So c must be in the natural domain of the tangent function. Now, if I draw the tangent function, you may remember that it has breaks. For example, there's a break here at pi over 2 and minus pi over 2. The tangent function comes up like this and is asymptotic at both sides. Then it repeats on either side to infinity in both directions. And so this may cause you to say, wait a minute, the tangent function is not continuous. It is not continuous because it breaks at minus pi over 2 and pi over 2 and for infinitely many other places. But remember what we said. The tangent function is continuous on its natural domain. The tangent function is not defined at minus pi over 2, nor is it defined at pi over 2 or any of those other places. And so those points are not part of its domain, which means that the statement is correct. The tangent function, the limit of the tangent of x equals tangent of c, as long as c is one of those points that are in the domain. And it's not one of these minus pi over 2 or pi over 2 or any of the other points. So you have to read carefully. This says that on their domains, the trig functions are continuous. If you ask if they're continuous on all the real numbers, the sine function would be continuous, the cosine function would be continuous. The others will not be. So just keep that in mind, and this is just more or less a lesson in a little bit of careful reading. Now we'll ask the question, when are inverses continuous? We're introducing this here because we'll be using it later. So the question is, when are inverses continuous? And here is the note I want to make, and I'll write it in the form of an if-then statement. If the inverse of a continuous function exists, so you're guaranteed to have a function that has an inverse. If that exists, then it too is continuous. So this is like another operation you can perform on a continuous function. If the function happens to have an inverse, then its inverse too is continuous. And the idea is very simple. If you remember, when we looked at graphs of functions that had inverses, for example, a function like this one, if this were the original function, then how would we get the graph of the inverse? Well, we take the graph of the original function and we simply reflect it across the 45-degree line, or that's the y equals x line. Now, if I do that here, I will try and do this more or less correctly by hand. Something like that happens. Notice that this inverse function graph is just as continuous as the original one. If the original one had no breaks, then neither does the inverse function. But let me give you a better example, one more familiar. A better example of this is to use inverse functions that everybody knows. Here is the statement we can make here. Since e to the x is continuous, we'll think of e to the x as our original function here, then its inverse function, which we know is the natural log of x, its inverse, is also continuous. Now, I didn't need to tell you that because you know from the pictures that that's true. Here's e to the x passing through 1. Here's the y equals x line. And here's e to the x. And here is the natural log function, which is its inverse. And you can see it's a reflection across the y equals x line here. And we already know that both of these are continuous from our previous experience. So this just verifies the notion that if you have a continuous function that has an inverse, then its inverse will also be continuous. Now we're going to talk about a technique of taking limits that's really extremely useful. In a sense, you take the limit without actually taking the limit. We'll call this finding a limit by squeezing. So to set the scene here, let's remember an old problem that we've seen before when we were talking about limits, which is, how do we calculate something like the limit as x approaches 0 of sine x over x? Now, the problem here, of course, is that the function, which is sine x over x, does not exist at x equals 0. So we cannot just substitute in 0 and hope to get a limit here. That simply doesn't exist. However, as we saw once before, if we look at the graph of this, this suggests that there is a limit there and that we ought to be able to find it. But how do we calculate it? Our previous techniques don't really help. The answer here, which is one possible answer, is we squeeze. Now, I will do this example later, but let's go ahead and look at the theorem that allows us to do this, named appropriately enough, the squeezing theorem. And the squeezing theorem goes like this. Again, I'm quoting this first to see if you can practice learning to read and develop for yourself pictures that will reflect this. Then on the next page, I'll show you a picture that shows the basic idea behind this. Most of the ideas in calculus are visual, and this is the way of writing them down. So let us suppose we have some functions that have this property. Suppose g of x is less than or equal to f of x is less than or equal to h of x for all x's not equal to c. We don't really care what happens at c. In some open interval containing c. And now let me stop for a moment here. we have an open interval that has this point C in it, and the functions are arrayed this way. So if I were to think of a picture, I'd say the graph of g of x is always below the graph of f of x, and that in turn is always below the graph of h of x. So even without going any further, I'm beginning to develop a picture of what this is. Now here is the second hypothesis. I will also assume that if I take the limit of g of x, which is the bottom function, see the bottom function here, as x approaches c, I get some number, which I'll call L. That will turn out to be, in my hypothesis, also the limit of h of x, which is the top function, as x approaches c. So I will assume that those two limits are the same. And then you can even see what's going to happen next. If f of x is caught between these two functions everywhere, and these two functions have the same limit at c, then it seems natural to expect, and it in fact is true, that the limit as x approaches c of f of x equals L too. That is what's known as the squeezing theorem. The limit of f of x is squeezed between the g of x and the h of x limit. So if you want, you can call this part of the theorem the squeeze. All right, what is the graphical idea? Well, I've already indicated it verbally. Here is a picture you might draw for yourself. Let us pick a point C, and we'll imagine that it's in some open interval here, and that we have three functions. So let me put a dotted line here so I know where C is. When we have three functions, we have a lower function here, g of x. We have an upper function here, h of x. And their limit, and this point in the middle where their limit is as x approaches c, need not even exist. This could be a hole. So this could be a hole, because the limit is all about the approach, not the destination. And then where is the f of x function? The f of x function is always between the other two functions. So if I label these at both ends so you can follow, I have f of x caught between h of x and g of x all throughout some open interval in here, say from there to there, and the limits of the outer functions at c are identically the same. And what is that height? That height is the value L. So f, since it is caught between those two, must have the same limit. And that's all that the squeeze theorem says. It is as simple as that. Now we're going to use it for something interesting. Now we'll use our squeezing theorem to find a couple of very familiar limits. Sine of x over x actually goes to 1 as x goes to 0, and other limit tails. So let's look at this first one. And rather than do this in complete generality, that is to say two-sided limit, I'll just do one side as x approaches 0 from above of sine x over x. And I will show you that that equals 1. And I'll give you the note that the x approaches 0 from the left proof is similar. So you'll see the main parts of this here. So we'll just imagine that we are only dealing with positive x's, which are angles here, and let them approach 0 from above, and I'll show you that the limit is equal to 1. So here is the proof of that fact. Now later, when you take Calculus 2, for example, you're going to learn a much more advanced limit rule, which will allow you to do this much more quickly. Right now, however, all we have is the squeezing theorem, so that's what we'll use. In order to do this argument, I'm going to have to rely on some geometry. So let me draw here a quarter circle, and then we'll have an angle coming out of here. This is the angle x because I'm talking about sine of x. I'm going to think of x as an angle here. All right. Then I want to label a few things. I'll label this point where it strikes the quarter circle as P. I will assume that this circle is a unit circle, so it has a radius of 1. I'll label the origin point with an O, and I will draw a vertical line here from where the quarter circle strikes, which I will call A, by the way, here. Call this point up here T, and drop a vertical from P down to the graph, the x-axis here. Well, I better not call it the x-axis. I'm using x for the angle. This is the horizontal axis. And this distance here, by the definition of cosine, is going to be that distance. And then the distance here to A, since it is 1 radius, is a unit distance. And I will then connect P and A here in a line like so. This vertical distance from the horizontal axis up to P, just as the horizontal was cosine x, this vertical is sine of x. Now in this picture you can see that this triangle OPA is totally contained within OPA, the sector, and that in turn is totally contained in OTA, the larger triangle. And that is the argument I'll be using on the next page. I'll need another fact from this picture, so let me go ahead and draw it over here. Let me pull out of this a couple of triangles here. There's one and there's another. And when I label them, you'll see where they are. There's P, T, this is A, and this is O. This distance here is cosine of x. This longer distance is 1. This distance here is sine of x, and I'm interested in finding some expression for the distance from A to T. Now notice that these two triangles are similar triangles. That means all three of their angles are identical. And you can see that easily. They have two right angles and they share this one, which makes the third one the same. Since that's the case, then the ratio of sine to cosine is going to be the same as the ratio of this unknown side to 1. So sine of x over cosine of x is equal to the unknown side over 1, which means that the length of the unknown side is sine x over cosine x. Now with all of that set up, I'm now able to come up with an argument that will allow me to find this limit. You may be wondering where this limit's going to come out of this. Here's what's going to happen. As I mentioned a moment ago, we have those three nested areas. So the area of triangle OAP is certainly less than or equal to the area of the sector of the circle OAP, and that in turn is less than or equal to the area of the larger triangle OAT. And before I go any further, let me bring the picture back and point out again what we have here. Triangle OAP is this triangle inside. OAP, the sector, is a little bigger, and OAT, the triangle, is bigger still. So the areas are nested in that way. And I now have an expression for AT, which I just figured out here, as sine x over cosine x. So continuing here, the area of a triangle is 1/2 the base times the height. So this is 1/2 times the base, which in this case is 1, times the height, which is sine x. That's less than or equal to the area of the sector. Now the area of the sector it's a proportion of the area of the circle. The circle's area is pi r squared, which is pi 1 squared. It's a unit circle. And what proportion? Well, the proportion that x is out of the entire angle of a circle, which is 360 degrees or 2 pi. So this is the area of the sector. The area of the triangle, again, is 1/2 base times height. The base is 1. And the height, as we just learned, was sine x over cosine x. Now with that written down, I can now simply do some algebra and then bring the squeezing theorem in. You'll notice there's a 1/2 common to all of them. And what I will do is I will multiply through by 2 to get rid of the 1/2. In the middle one, notice that pi over pi will also be equal to 1. And I will do one other thing. There is a sign here on the left and a sign here on the right, and I will divide it out. So what I will do here is I will multiply by 2 over sine x. What will that leave me with? Here it will leave me with a 1. In the middle, it will leave me with an x over sine x. On the right, it will leave me with a 1 over cosine x. Then if I flip these all over by taking their reciprocals, which of course will reverse the direction of the inequalities, I'll have 1 greater than or equal to sine x over x, greater than or equal to cosine x. And you see that the sine x over x has turned up. Now, observe that if I take the limit of 1 as x goes to 0, I get 1. Well, of course, 1's a constant. It doesn't matter what x does, 1's not going to change. On the other end, if I let x go to 0, which means I'm taking the limit of cosine x as x goes to 0, that is equal to the cosine of 0, and that is also equal to 1. Now, if you think of this left-hand side as the g of x from the original theorem, and this side is the h of x, then we have this f of x function caught between. Since the two limits here go to the same place, we can say thus, by squeezing, using the squeezing theorem, we get that the limit of sine x over x as x approaches 0 is in fact equal to 1 because it has to be the same number as the two ends. So there we have it. Going back to the original page for a moment, you see that using this geometric argument, which took a bit of work, we found out that the limit as x approaches 0 from above, that's because I'm thinking of the angle as moving down this way, from a positive angle down towards 0, the limit is equal to 1. And it came out of this argument starting with geometry and ending up with the squeeze theorem. Now, we would prefer not to have to spend that much work doing limits, and later we'll learn a way to avoid that. But this is such an important limit that it was worth looking at in detail. Now, as a second example here, let us do another well-known limit, and this one will be much easier because of all the work we just did. The limit of 1 minus cosine x over x is in fact equal to 0. Again, this is not an obvious limit because if x goes to 0, you're dividing by 0, and we have difficulties there. In fact, it's even worse than that. Cosine of 0 is 1, so we get 1 minus 1 or 0 on the top also. So we really do have to do some work here. Well, in this case, as I said, we get to use the result we just proved, and that will save us a lot of work. So the limit we're looking for is the limit of 1 minus cosine x over x. In order to get the sign involved, which is what the previous limit uses, I am going to do a little bit of algebra here. Notice that if I multiply the top and bottom by 1 plus cosine x, the top then becomes 1 minus cosine squared x, and the bottom is x times 1 plus cosine x. Well, 1 minus cosine x is a familiar identity. That's equal to sine squared. And so the sine has now found its way into this problem. Sine squared x over x times 1 plus cosine x. And then all I have to do is tease that apart and write the limit as x approaches 0 of sine x over x, which is a limit I just figured out. And then what's left? I have a sine x left because it was sine times sine for sine squared. And on the bottom, 1 plus cosine x. Well, the first part goes to 1 by the previous work. The second part I don't have any data on, but this is a limit I can directly figure out. The sine is going to go to 0. Then I'll have 1 plus, this goes to cosine of 0, which is 1. And 0 over 1 plus 1 times 1 gives me 0, which is exactly what I expected. So by doing that famous limit and then applying it here, I get a second very useful limit that we will see from time to time. Now we'll do some exercises. And as the first one, I'll set you up with this. Suppose you're asked to take the limit of the tangent of 7x over the sine of 3x. See what you can do with that. Now let's see how we might think our way through this problem. Surely, because we just did a limit on how to calculate the limit of sine x over x as x approaches 0, since x is approaching 0 here, and there's a sign on the bottom, and in the definition of tangent there's a sign, you would expect that that limit is probably going to be used. The question is how? Well, the first thing we can do is sort of separate some of this out and get the sign that's inside the tangent visible. So let's just rewrite this, and this is algebra so far. Tangent of 7x is the same as sine of 7x over cosine of 7x. So we'll write that down. Sine of 7x over the cosine of 7x. And then that other sine of 3x, which is on the bottom, I'll just move over to the side here, times 1 over sine of 3x. Now, the next step is what I like to call wishful thinking. We'll call this wishful thinking. And what I mean is, why don't we write this out in such a way that it would be set up the way I would like it to be set up? For example, I see sine of 7x here. I would like there to be a 7x on the bottom, because then I'd have a sine of something over something, and if that something were to go to 0, and if x goes to 0, 7x goes to 0, then I'd be able to pull in that limit I did before. So I'll write down 7x, sine of 7x over 7x. Now I'm not going to worry about making this work out just yet. Let's just write down what I'd like to have. That's the wishful part here. Now, the cosine 7x, what about it? Well, I don't care about it. It was not involved with that last limit, and I'm just going to leave it as 1 over cosine 7x. Then again, sine of 3x is left here. I wish I had 3x on the top, so I will just write it in there. I'll write sine of 3x on the bottom and write a 3x on the top. Now, before I continue on, because I've done these wishful thinking operations, I have to make sure that I haven't just changed the problem. This expression here should be equal to this expression here. Now the sine, cosine, and the other sign here are all the same. Let's see what happened. I threw in a 7x on the bottom and a 3x on the top. Well, that works out nicely. X over x is 1, so that doesn't change anything. However, I did put a 3 on the top and a 7 on the bottom. That did change things. But I can easily fix that. If I multiply 7 over 3 out front, that 7 and that 7 will be 1. This 3 and this 3 will become 1, and so I now have not changed the problem. The advantage to this new arrangement, however, is that I can use my previous information. Here, the limit as x goes to 0 of sine of 7x over 7x is going to be 1. So the 7/3 stays here. This becomes 1 because these two go to 0 as x goes to 0. The 1 over cosine 7x, as x goes to 0, this goes to cosine of 0 in the bottom. 1 over cosine of 0 is 1. And then 3x over sine of 3x is just the reciprocal of sine of 3x over 3x. As x goes to 0, the 3x's go to 0. So again, I have 1. Or if you like, you could write it as 1 over 1. So all these 1's multiplied by 7/3 gives me 7/3. And that, in turn, is the answer to this question of what this limit is. Now, don't convince yourself that you found a fast way by saying if I have tangent over sine like this, I can take 7 over 3 and just pull it out front and call that the limit. Unless you prove that is true for all cases, then you don't know it's true for all cases. It happens to work here. But what you want to realize from this process of wishful thinking is, if you can get the famous limit in here, then you can have things go to 1. And let me rewrite that famous limit in a more generic form right over here, just so we're clear. The limit really is the limit of sine of box over box as box goes to 0 equals 1. I've replaced the x's here in the original statement by boxes to emphasize that whatever is in any one of these boxes, and is in all three of them, if it fits this pattern, the limit will always be 1. That's why this worked if these were 7x, 7x. And although this was x going to 0, it's the same thing as 7x goes to 0. And it also worked for 3x and 3x. So if you remember this, you'll be able to use this limit in other circumstances. So let's try another one. Here is a limit as t goes to 0 of t squared over 1 minus cosine squared t. Go ahead and try that, and I'll be back. For this problem, it is even easier than the last one. You may recognize here one of the limits that we proved earlier. So let me rewrite this for a starting place. You may recognize in here that there's a t over 1 minus cosine t lurking in here. Now to find it, I'll have to do some algebra again. Algebra is essential here. On the top, I have t squared. And I'm going to choose to break that into t times t. The bottom is the difference of two squares. 1 minus something squared breaks into 1 minus the something, 1 minus cosine t, times 1 plus that something, 1 plus cosine t. This is the limit we proved earlier. If the t goes to 0, this expression goes to 0. So this is equal to 0 times whatever this goes to. Now, don't automatically assume that because this goes to 0, this expression doesn't matter. It does matter. This expression, if it were to go to infinity, for example, would cause difficulties here because 0 times infinity is not defined. So you actually have to check and see where this goes. In this case, as t goes to 0, notice that the top goes to 0, then it's 1 plus the cosine of 0 on the bottom, which is another 1. That is 0. So 0 times 0 is 0, and this limit is very simple. But what we got to use here was a previously done limit, and we wanted to recognize that you need to actually figure the other part out, not assume that 0 times anything is 0. 0 times an infinite expression is not necessarily 0. So with that, we'll leave our story of limits.